In the deepest reaches of space, far beyond the shimmering veil of stars that define our night sky, there exist colossal structures, so massive, so ancient, that they bend the very fabric of reality. These are not galaxies. They are galaxy clusters, vast, gravitationally bound congregations of hundreds, sometimes thousands, of galaxies swirling together in cosmic dance. Each cluster is a city of galaxies, and each galaxy, in turn, is home to billions of stars. To find one is to witness a monument of time itself. And so, astronomers hunt them, not with nets or ships, but with telescopes, algorithms, and patience. The hunt for galaxy clusters is not merely an effort to map the sky. It is a quest to understand how the universe assembles its largest structures and perhaps to peer into its deepest secrets. A galaxy cluster is more than a gathering of stars. It is a gravitational ecosystem, a massive knot in the cosmic web where the universe's invisible scaffolding tightens and tangles. These clusters are the largest structures in the cosmos held together by gravity. Within them, hundreds or even thousands of galaxies orbit a shared center of mass, like bees circling a hive. But most of the mass in a galaxy cluster isn't stars, or gas, or dust. It's something else, something unseen. Nearly 80% of a cluster's total mass is dark matter, an invisible substance that does not emit, absorb, or reflect light, yet reveals itself through its gravitational pull. And surrounding all of this, the galaxies, the dark matter, the hidden architecture, lies superheated gas, reaching temperatures of tens of millions of degrees. This gas glows not in visible light, but in X-rays, creating a diffuse halo detectable only with specialized space telescopes. In short, galaxy clusters are cosmic giants, and to find them is to trace the fingerprints of the universe's underlying structure. But why search for something so distant, so hidden, so massive? Because galaxy clusters are not just relics of the universe's past. They are keys to understanding its future. Their distribution tells us how matter has clumped together over billions of years, guided by gravity, shaped by dark matter, slowed by gas, and stretched by cosmic expansion. By studying their formation, scientists can test our models of cosmology. How fast is the universe expanding? How much dark matter is really out there? What is the nature of dark energy, the force believed to be accelerating cosmic expansion? The number of clusters we see at different distances, different points in time, helps refine our answers. In this way, galaxy clusters are more than beautiful structures. They are scientific instruments, natural observatories embedded in the cosmos, each one a chapter in the universe's long story of growth, collapse, and rebirth. Hunting for galaxy clusters requires more than just a telescope. In fact, it takes an orchestra of instruments, each tuned to a different frequency of the universe's symphony. Optical telescopes scan the sky for concentrations of galaxies, looking for dense patches where galaxies cluster together. But this method alone can be misleading. What looks like a cluster may simply be a chance alignment. Galaxies lined up along our line of sight, but separated by millions of light years. To separate illusion from reality, astronomers turn to X-ray telescopes, like NASA's Chandra or ESA's Newton, which detect the hot intracluster gas that only exists in true gravitationally bound systems. Then there's the Sunyaev-Zel'dovich effect, a phenomenon observed in the microwave spectrum. When cosmic microwave background photons pass through a galaxy cluster, they scatter off the high-energy electrons in the hot gas, leaving a distinct fingerprint. Instruments like the South Pole Telescope and Planck satellite detect these tiny shifts. Finally, gravitational lensing, the bending of light by mass, provides a way to map the invisible dark matter in and around clusters. When distant galaxies appear distorted or magnified, it tells us something massive, yet unseen, lies between us and them. The hunt, then, is multidimensional. We are not just looking for light. We are mapping gravity, heat, and time itself. When we observe galaxy clusters, we're not seeing them as they are today. We're seeing them as they were, millions, sometimes billions of years ago. The light from a cluster a billion light years away began its journey when Earth was teeming with early life. Light from a cluster 10 billion light years away began when galaxies were still assembling and Earth had not yet formed. In this way, every cluster is a time capsule, a frozen frame in the movie of the universe's evolution. By piecing together clusters at different distances, we can construct a kind of cosmic time-lapse. We see how matter came together, how galaxies collided and merged, how clusters grew from small groups into titanic structures stretching millions of light years. We witness, in snapshots, the architecture of creation, and through it, we glimpse the silent, relentless hand of gravity shaping the cosmos across eons. Galaxy clusters are not just milestones in the cosmic timeline, they are also mirrors. Mirrors that reflect the hidden forces governing the universe. The number, size, and distribution of clusters help us measure the contents of the cosmos. How much is ordinary matter? How much is dark matter? How much is dark energy? If the universe had more or less dark energy, galaxy clusters would be more or less common at different epochs. Clusters also help refine the Hubble constant, the rate at which the universe is expanding. When compared with data from other methods, they sometimes show puzzling discrepancies, hinting at possible cracks in our cosmological models. In short, galaxy clusters are a laboratory, an experimental arena on the grandest scale, one where we test not just our understanding of astrophysics, but the very shape, fate, and origin of the universe. And yet, the hunt is far from over. New surveys are beginning. The Euclid Space Telescope, Rubin Observatory's LSSD, and eROSITA are mapping the universe with unprecedented precision, revealing thousands, perhaps millions, of previously unknown clusters. Each one sharpens our view. Each one adds a pixel to the cosmic image. But there are deeper mysteries still. Some clusters bend light more than their visible mass suggests. Some form earlier than expected. Others seem to resist the models we've built. These outliers are not failures. They are clues. Clues that the universe still holds secrets we do not yet understand. Why do we hunt galaxy clusters? Because they are the bones of the universe, the skeletal structure upon which all else is built. Because they carry the echoes of ancient collisions, the glow of forgotten stars, the imprint of invisible forces. And because, by studying them, we study ourselves. Our desire to understand the universe is more than scientific. It is spiritual, philosophical, existential. In the gravity of clusters, we see a metaphor for our own search for connection, for belonging in something larger, something cosmic. We are made of the same matter. We are shaped by the same forces. And so we look to the sky, not just to know what's out there, but to remember where we came from and to imagine where we're going. Thank you for joining us on this journey through the cosmic web, through gas and gravity, through time and light. The clusters are out there, still forming, still merging, still glowing softly in the silence of space. And we will keep looking, because the universe is not just something to observe, it is something to understand.